Thank you, Shui, for this very nice and kind introduction, and thank you also to Bernd, Antonio, and George for inviting me here to this very beautiful place. And I have to say that I always enjoy being part of Chemnitz Symposium on tour or in Chemnitz. Doesn't matter. I really like to participate here and really enjoy it. Today, I would like to present you some recent results together with my former PhD student, now postdoc, Anne Wald. It's about efficient minimization tool also in Hilbert and in Banach spaces. It's a so-called sequential subspace optimization technique, which we are working for now since 5 or 6 years. And an application of this method to the novel technique in terahertz imaging. First, a short overview of the contents of my talk. I'd like first to introduce you to these two concepts, sequential subspace optimization and terahertz tomography. And then we come to more details from some basic notations and definitions of this sequential subspace technique. And then we talk about also the regularized version, which shows that this method is also appropriate to stably solving inverse problems. Here we have a Hilbert space setting, a nonlinear problems in Hilbert space setting, but we are just extending this method to Banach spaces too, which should be finished at the end of the year. Terahertz tomography is an application which is maybe not so old and maybe not so convenient to most of you. So I tell a little bit about the physical background and how to get a mathematical model of this method. And then we want to apply the results of the section 2 to this problem for reconstructing the complex refractive index of a specimen. Some numerical results and in conclusion will finish my talk. Though the first part of my talk is more a theoretical framework for efficiently solving linear or nonlinear problems in Hilbert spaces, especially. In a linear case, we already extended this method to Banach spaces. In the nonlinear case, as I told you, this will be, the work will be finished at the end of the year or beginning of next year. And the first idea to develop this method was the following. We always observed that the very well-known Landweber method shows to be very stable with respect to noise, but tremendously slow in numerical applications. And this situation is even worse in some Banach space settings, like, for example, L1 settings and so on. So we thought of using an idea which maybe also comes from a method of conjugate gradients, that you use not only one search direction, but more than one search direction. This is a basic idea of the sequential subspace optimization techniques, where first ideas go back to Nanakis and Cibulewski. They used such a technique to minimize functionals, and we used it to solve operator equations, linear and now nonlinear ones. Terahertz tomography is a pretty novel method. It uses part of the electromagnetic spectrum, which we haven't been taking so much attention so far. I mean, if you go up to longer wavelength, then you are in the submillimeter region or in the radio wave region, and you all know applications for that. Even if you go to higher frequencies, you find visible light and then X-ray techniques and X-ray tomography. But what about the terahertz regime? Terahertz waves show to be very sensitive with respect to moisture. And it's used to monitor defects in such specimens like ceramics, for example. It's not appropriate, for example, for medical diagnosis or something like that, because terahertz waves do not penetrate the human body. And this is why they are used, for example, in body scanners at airports, which you all well know by now. These terahertz waves or waves in the submillimeter regime. The reason is that you can have a very small penetration depth to guarantee that you do not see the entire human body. But hidden objects beneath some clothes, for example, can be detected, but not more. So this makes it interesting also for body scanners. The second part is also a cooperation with the German Plastic Center in Würzburg, who built up a terahertz scanner, which was funded by a common AIF project, so funded by a ministry, a German ministry. Okay, so let's start with the sequential subspace optimization. I will really start from the very beginning. So first, use some notations. Well, we use a Hilbert space setting here with two Hilbert spaces x and y. And we always denote the set of solutions by this capital M, with fx equal to y. It's a set of all solutions, and f is a nonlinear operator defined on some domain D of f. Of course, we also assume to have noisy data where noise level delta is greater than, or can be estimated from above by this difference to the exact data. This is quite common assumption. In our method, we use some more notations, namely hyperplanes, half spaces, and stripes. So if you have a vector from x, which is not equal to 0, and two real numbers where c is non-negative, then of course we can define an affine hyperplane by this set, where u is a sort of normal vector, or whatever. If you consider all x where the inner product, this is always the inner product in the corresponding space. I dropped the subscripts for better readability. And the inner product of u with x is less than alpha, then you get a half space. And of course, a stripe if the distance is from a given alpha is less than xi. All this will play a key role in constructing this technique. Okay? So, motivated by Landweber's method, we now define SysOp iterations in the following way. First, I describe the results for linear operators, and then we extend this method to the nonlinear case, and you will see some deciding differences between the two cases, and why the nonlinear case is much more complicated also in the construction of the method for exact data. Okay, it's an iterative method where the new iterate is computed from the old iterate, xn, by a linear combination of search directions, which are in the range of A star. So if you, for example, use Weni equal to A xn minus y, you get Landweber's method if you use this as a single search direction. So Landweber's method with a specific step size, t and I, is contained in this construction. It's a special case. But here, the step sizes tn are now chosen in the following way as to solve this quadratic functional, this function hn of t, which, where t is from a finite dimensional space, Rm, where m is a number of search direction in In. So you have a finite number of search directions in each step in the range of A star, and you solve this quadratic problem. And the question is, why do we solve this problem to have the step sizes? Now, the answer is the following. If we minimize h and t to get the step sizes t and I, we just compute in each step a metric projection of the old iterate, xn, to an intersection of finitely many hyperplanes, h and y, where h and y is just the hyperplane with a normal vector equal to the search direction. So the search direction is normal vector, and the offset is given as the inner product of the pre-image w and I with the exact data y. And obviously, any solution of the linear equation is contained in this set. Just skip A star to the right-hand side, use AX is equal to Y, and you see any solutions contained in this hyperplane. And so it's also contained in the intersection of all hyperplanes. And so there's hope to get convergence for n going to infinity. This is exactly where this function comes from for the step sizes. This is essential, that t and I is solved as a solution of this quadratic function. One can also prove that if the search directions are linear independent, then this quadratic functional hn has a unique solution. This is not very difficult to prove. If we have noisy data in the linear case, we are still in the linear case, if we have noisy data, then we do not project on half planes, rather but to stripes, where the width of the stripes, this is its xi, depends on the noise level. And still, the solution set is contained in any of these stripes. This is the key idea, how to make this method to a regularization method for noisy data in the linear case. These are the key ingredients. Okay, so in each step, what you have to do, you have to choose some search directions. You have to solve a quadratic functional without any constraints, so unconstrained optimization. That's not too difficult. You also can compute the optimality condition, and you get an explicit representation of the solution. It's not a problem. And then get the new iterate by this expression. So the question is now how to extend these results to the nonlinear case. Okay, there are some basic assumptions to F, to the forward operator. Anybody who has done research in nonlinear inverse problems knows these conditions. The first one is the so-called tangential cone condition, where this constant here is assumed to be less than 1 and positive. And we furthermore assume some sort of uniform boundedness of the Fréchet derivative of f, such that the supremum in some neighborhood of the initial value, b rho of x naught, is a ball of radius rho around centered about x naught, is bounded by a constant zf. So we cannot use hyperplanes here anymore to project on. The reason is that nonlinear operators, that this condition here will not be satisfied if f is nonlinear, obviously. So the idea is, even in case of exact data, use projections onto stripes. We just wanted to illustrate this situation by this picture. Here you see the actual iterate, and here this is a nonlinear mapping, f of x. And the idea is to use locally stripes by a given width xi n, such that in a neighborhood this fx is contained in it. And we have to take into account also the character of nonlinearity. That means this constant ZTC and the constant ZF to the width of the stripes. This is the idea to generalize this method to nonlinear mappings. Okay, this looks very wild, but it's not so bad as it looks. So we define our stripes to guarantee that the solution set is contained in it, in each step. This is the problem. We have still to guarantee that our solution set is contained in the stripes. Again, in the linear case, the stripes for noisy data were defined as follows. This is in a linear case. Here you see the noise level appearing in the right-hand side, defining the width of a stripe. In a nonlinear case, it looks a little bit more complicated. You use here to define the stripes the joint of the Fréchet derivative applied to this Brie image, defining the search directions. And you use noise level and this constant Z TC from the tangential cone condition. If you do that, it's straightforward to see that all the solutions of your nonlinear equations are contained in each of these stripes. This is the point. So don't bother the special form here. The key idea is what I want to tell you is that by this definition, the solution set is contained in each of these stripes we project on. Okay? And our regularized sequential subspace optimization technique is then defined as follows. With R&D, we always denote the residuum. And as a regularization a posteriori parameter choice rule, we use the Morozov discrepancy principle. And as long as this principle is not satisfied, so if the norm of the residuums are bigger than tau times delta, tau is a tolerance parameter, then we compute the next iterate by using the old one and then a linear combination of these search directions, where the search directions are all in the image of the adjoints of the Fréchet derivative. This is one-to-one extension of the linear case where we have just A star here instead of the adjoint of the Fréchet derivative. And by our theory, this is guaranteed that this is in the intersection of all the stripes defined as above. And as long as the discrepancy principle is not satisfied, we would know that we are in a, that the new iterate is a better approximation to all the solutions in the set M than the old one. And we can compute this factor here. It depends on the residuum, on the noise level, on the tangential cone condition, and this constant by the uniform boundedness of the Fréchet derivative. Okay, so the first thing we have to prove is convergence of our method if we have exact data, and then we have to prove the regularization property in case of noisy data. It's always the same game. Yeah? And to do so, we always assume that the actual iterate index n is contained in this index set n, which gives you the actual search directions. And as pre-image, we use the actual residuum for each index in this set in. And we have to assume that a solution, a unique solution, is in a neighborhood of our initial guess. I mean, that's maybe not that surprising, because if you have a nonlinear equation and you use iterate method, then you have a local convergence. And so you have to guarantee that there's a unique solution in this neighborhood of the initial guess. And the convergence theorem reads then as follows, the sequence of iterates generated by the setup algorithm converges strongly, even strongly, to this unique solution in the neighborhood of the initial guess if the optimization parameters are bounded. This is a condition which we do not like to have because it's very, very hard to check it. Yeah? We have a boundedness condition to our step sizes. But maybe it's also not that surprising that you have such a condition because even if you are close to your stripe on which you project, if the normal vector has a small length, then step size can be arbitrarily large on the projection. This is maybe a good illustration of this fact, but we needed to prove this strong convergence result, and we couldn't get rid of it. And my conjecture is that it's essential. Otherwise, you maybe can even construct a counterexample. Okay, so this is convergence. Next thing is the regularization property. If you construct a regularization method, you need a parameter choice rule, of course. And we chose a standard a posteriori parameter choice rule, the well-known discrepancy principle, where the tolerance parameter is chosen that it is greater than this, this fraction, where the constant again of this tangential cone condition appears. And if we choose this discrepancy principle, the first thing we can prove is that it yields a finite stopping index, depending, of course, depending on the noise level. The second thing we can prove is stability. That means if you have a fixed noise level, excuse me, not a fixed noise level, a fixed iteration index, so fix n, and then you can prove convergence of the regularized solution to the iterate xn of the exact data. This means stability of your method. And last but not least, we also have a regularization. That means our algorithm yields a regularized solution where the stopping index depends on delta. It's just the stopping index coming from Morozov's principle. And then for delta tending to 0, you get this unique solution, which is unique in the neighborhood of initial guess. But also here, such a boundedness assumption appears. We have to postulate that the limit of all the step sizes when delta tends to 0 remains bounded. Yeah, that's essential for this proof. And maybe this is a little bit unsatisfactory. If you think about standard proofs for Landweber's method, as for example the book of Bernd Hofmann, Barbara Galtenbacher, and Andreas Neubauer, there's not such a condition, of course, no, such a boundedness condition. It must be in a certain range, but this is maybe a little bit new. Okay. So this was the extension of our method to nonlinear problems. And why did we do that? Well, our problem we consider together with the German Plastic Center is a nonlinear inverse problem. It's a nonlinear parameter identification problem for the Helmholtz equation. So what is terahertz tomography? Now, that's the second part of my talk. It's a rather novel imaging technique. I hesitate a little bit to say that because engineers use it, but not in this way we do. They just took some known inversion methods like filtered back projection and got some results which were not very satisfying. So we developed a decent mathematical model relying on some physical phenomena. Terahertz waves are non-ionizing. That's good, and so there's no harm for anyone working with it. And we speak about the terahertz range if we have a frequency of our electromagnetic waves between 0.1 and 10 terahertz. Terahertz beams are usually modeled by Gaussian beams. And this is maybe a very good model for them, because if you go far away to X-rays, you always have, or you can neglect the wave character of the beams. Yeah? That is why we have the radon transform as a mathematical model of X-ray tomography, because we neglect the wave character completely, and we're talking about lines. Yeah? If you go to longer wavelengths, like radio waves, for example, you cannot neglect the wave character. Yeah? Terahertz waves are in the middle of that. So if you here have a plot of a Gaussian beam, the name comes from, if you make a cut here by the x direction, you get a Gaussian profile of the beams, where you have a Lorentz profile in the y direction. And it has a waist here, and you see it, you have small aberrations in the x direction from the wave being just aligned. So these Gaussian beams solve the so-called paraxial approximated wave equation. That means you assume to have only small deviations up from the direction of the wave vector. And then you come to the Gaussian beam. And this is what we included to other mathematical model. So we put Gaussian beams to a specimen under consideration. So here is our specimen modeled by domain omega. And in the German Plastic Center, they constructed a terahertz scanner consisting of 4 transmitters and transducers, and they can rotate around the object. This is why we have here several detectors and transducers by this EJ1, EJ2, and so on. And from each transducer, we send a Gaussian beam to the object. Then you have reflections, you have attenuation, and you have transmission. Yeah? So you have all these phenomena which play not a role in X-ray tomography. You find them here. Yeah? And the inverse problem of terahertz tomography reads as follows. From all these measurements at these detectors, from transmissions and reflections, reconstruct the complex refractive index of the medium. That means the refractive index as well as the extinction coefficient. And it's very interesting for engineers, for example, because these electromagnetic waves are very sensitive with respect to moisture. So you have inclusions or moisture could be detected for ceramics, for example, or polyethylene and so on. This is what they consider. Okay, so we need a mathematical model. So for convenience, we do not consider the refractive index, but the difference, m of x, which is 1 minus n tilde. The reason is that this function, of course, has a compact support inside. So the domain omega, which has a smooth boundary. And then we can model it by this boundary value problem. We have here the Helmholtz equation for the scattered field. And our source field, Uy, is a Gaussian beam. So it's a Gaussian beam. And this is a boundary value problem for the scattered field. We assumed Robin conditions here. The reason is the following. We measure here our radiation, and we cannot assume now to have Dirichlet data or something else. But we have to use so-called perfectly matched layers, and they are modeled by these Robin conditions. And of course, our total field is the sum of the scattered field and the incoming wave. Well, and given the measurements at the detectors, we have now to compute M from this system. Okay, first of all, we have to prove that this system has this PD has a unique weak solution. And well, doing so, we assume that M is bounded, essentially bounded, and its imaginary part is less than or equal to 0. This is not quite restrictive because from a physical reason, this is obviously the case. And we considered this Helmholtz equation, the boundary value problem, and got a variation formulation. And then we can prove that this boundary value problem has a unique weak solution in H1, and this solution is bounded by the L infinity norm of M and the L2 norm of the Gaussian beam. The constant is not depending on M or U. Now we define the scattering operator, which we use for the inverse problem. The scattering operator is supposed to define on this domain. That means we take all the m's which are bounded by capital M, and imaginary part of m is less than 0. And this scattering operator maps an m to the total field, which is the sum of the Gaussian beam and the scattered field. And UFSC is the weak solution of this boundary value problem, which we considered before. Then we can prove first that this scattering operator is well-defined first, and it's Lipschitz continuous, which is stated by this inequality, where this Z2 depends on the wavelength K0 and the domain, that's some properties of the domain, but not on M1 or M2. S is even Fréchet differentiable. This, if you consider the Sesop algorithm, you need the Fréchet derivative and its adjoint. So we have to compute the Fréchet derivative next. And this is done by standard arguments. You first compute the Gateau derivative, and then you show that's even a Fréchet derivative. And doing so, you see that this derivative here is given as a solution of this linear problem. Any h is mapped to the solution W of this problem, which is so-called the dual problem to our boundary value problem. And of course, although this problem has a unique solution. And even more, we could prove the tangential cone condition for the scattering operator. That means that if we compare this linearization with the difference of these values for two different refractive indices, M1, M2, you can estimate this by a constant times the difference of the images. And this constant, again, depends on K0, the wave number, omega, and M. Okay, so now we have almost all ingredients together to apply our Sesop algorithm. We just went all the way from mathematical modeling and then tackling the inverse problems. But now in real-world applications and in these measurements from the German Plastics Center, you, of course, do have only finitely many data, measurements data, at these detectors EJ1 to EJM. So the emitters are rotated on a circle around the object, and the incident field UJ1 depends on the position then. Again, if we look to this picture, you have here rotation about this origin, and from each such detector you send out a Gaussian beam. So of course, data depend on the position. There are finally many positions, and the same, of course, holds for the scattered and the total field. So to describe now our problem completely, we have not only the scattering operator, we have also a so-called observation operator to take into account. So the nonlinear forward operator consists of this tuple of measurements, where to each position of the detector we have the scattering operator, then we have the trace operator, which restricts our solution of the Helmholtz equation to the boundary. This is a standard trace operator. And then you have this observation operator Qj, which just computes these detector measurements as small averages about small parts of the boundary. And this is now the complete forward operator. Since Qj and the trace operator are linear, it's easy to compute the Frege derivative, and it's a joint in that way. Okay, so now our inverse problem reads as follows. Compute M as solution of all these nonlinear equations where we have noise level delta. Okay, and we have to compute the gradient, all that, of our truss data fitting functional. And, well, Fj star is obvious because Qj and gamma are linear. It's just this mapping. And if you compute the adjoint, well, we get just the adjoint of this operator and Qj. Why do we put the trace operator in here? Because it's pretty easy to compute the adjoint operator by solving, again, such a boundary value problem. This was inspired by an article of Gang Bao, who did this in a similar regime. Okay, now everything is together. We have now the adjoint of the Frege derivative of all our forward operators given by this function here, and we always have to solve such a boundary value problems where the measurement process is included here as a right-hand side of a Robin condition. And our method looks as follows. For example, again, Landweber's method would be just take the old iterative and then have here a search direction of steepest descent with respect to the residuum. And what we do now here is we use average gradients and use the CSOP algorithm in complex Hilbert spaces because a refractive index is a complex number. And so CSOP has to be adapted in a straightforward manner to be usable for also in complex Hilbert spaces. Okay, some numerical results at the end. We have 3 different refractive indexes here. We have a square specimen with 2 inclusions of different complex refractive index. We are at the lower bound of the terahertz regime, applying a frequency of the Gaussian beam of 0.1 terahertz. We have 180 detectors and use equal to 40 directions, and then this is the value of the tangential cone condition, which has to be guessed in some way. Of course, we do not know it exactly, only some estimates, and as tolerance parameter we use tau equal to 20. Okay, and if we have 2% noise, then we see here a reconstruction of the real part of M, which is a refractive number. And we see here the reconstruction of the imaginary part. And you see 2 things. Refractive index is reconstructed pretty well, where the extinction coefficient is reconstructed pretty bad. We have here 30 iterations, and this is computing time on our computers. But maybe it is also very interesting to compare CSOP with Landweber's method. And here you see the exact solution. You see here the results with Landweber, and here the results with Recessop. And in both cases, Recessop delivers better reconstructions and even a quicker reconstruction with respect to computing time. So for Landweber, we needed 155 iterations for the discrepancy principle to be satisfied, and more than 5.5 hours. And for Recessop, just 20 iterations and only 1 hour. Okay, I conclude. So we succeeded in extending Recessop to nonlinear operator equations in Hilbert spaces. We had proof of convergence and regularization. There are even new ideas to use so orthogonal directions, so you get one more step to Ziggy conjugate gradient methods also in Banach spaces. And future research would be the extension to nonlinear inverse problems in Banach spaces and a hybrid algorithm which combines an art technique which we developed here at our Institute for terahertz tomography and these techniques which I have presented in my talk. Okay, here's some very important literature which was inspiration also for us, especially the article by Gang Bao and Li, and some other articles. So I thank you for your attention.
Okay, thank you for a very nice talk. We have time for one or two quick questions.